This is the last video for this section. It's on electron configuration in the periodic table, or why the periodic table has the shape it has. I'm going to start by defining valence electrons. Valence electrons are the electrons in the highest primary energy level when the atom is in the ground state. The maximum number of valence electrons for any atom is 8. You can't have fewer. And valence electrons are in the s or p orbitals, never in the d or f. For example, sodium has this configuration. You notice that the highest energy level is the third energy level, that the orbital being filled is the s orbital, and there is one electron in the s orbital. So there's one electron on the highest energy level. Sodium has one valence electron. Bromine, with this electron configuration, you notice that the highest energy level is 4. There are 2 electrons in the s orbital, 5 in the p orbital, total of 7 in the highest energy level. Bromine has 7 valence electrons. I'm going to try and show you how this relates to the periodic table, and this will be important in the next section when we start talking about ions and ionic compounds, and we will most definitely review this. This is the periodic table we are used to seeing. It's hanging up in pretty much every science room in the world, or at least in the United States. You have copies of this, and you can think that it almost looks like a castle, with turrets being the representative elements, the tall columns. But this does not have to be the shape of the periodic table. There have been other periodic tables proposed. There's the Starship Enterprise. And if you start in hydrogen, what you will notice is you have a spiral, and the spiral follows the atomic number. And lining up, at least in the main part, are all of the groups. There's the circular pattern. This could be used. There's the pyramidal, and if you follow the line, you see that the line goes in a spiral form, following an atomic number. But the general consensus is this is the most useful method, and since it's the one we're familiar with, it's the one we're going to work with. So why does the periodic table we use have the shape it has? We're going to start by looking at the representative elements, groups 1, 2, and then 13 through 18. And we'll start by looking at the noble gases, group 18. And here is the electron configuration for all of those elements. If you look, you will note that they have a completely filled valence shell. And once you get past helium, they all consist of something S2, something P6. They follow a periodic pattern as far as electron configuration goes. Is this a coincidence? Well, let's take a look. Let's look at the alkali metals, first grouping. But we're going to include hydrogen here, even though it's not an alkali metal. Look at the electron configuration. Here they are. And then look at the valence electrons. And you note that every element within the group has a similar configuration for their valence electrons. How about the alkaline earth metals? Here's the electron configuration. Here are the valence electrons highlighted. And lo and behold, once again, it is a similar pattern. And notice it's a periodic pattern. How about the group number 13, or the third group in the in the representative elements? There's the electron configuration. There are the valence electrons. And within the column, it's all S2P1. If you went to the next column, which starts with carbon, it'd be S2P2. The next column, S2P3. Until you come to the halogens, which have this electron configuration. There are the valence electrons, and they're all in S2P5. The electron configuration within a group is a periodic function, and within each group they are similar, not identical, but similar. So for the representative elements, the number of valence electrons is related to the column. And remember, we're talking about the tall columns in the periodic table. In the first tall column, or group 1, there's 1 valence electron. In the second tall group, or group 2, there are 2 valence electrons. In the third tall column, or group 13, there are 3 valence electrons. Group 14 has 4 valence electrons. Group 15 has 5. Group 16 has 6. Group 17 has 7 valence electrons. And group 18 has 8 valence electrons. Knowing the number of valence electrons and being able to take it off the periodic table will prove to be very beneficial in the next section. You can also break the periodic table into what are called blocks. The first 2 tall columns are the S block because the valence electrons there are all either S1 or S2. There's the P block. The valence electrons here are all S and P, and it goes in order. The transition metals are the D block, not because the valence electrons are D, but because the D orbital is finally being used. And then the 2 rows underneath the periodic table is the F block. Now notice the S block has 2 columns, and the S orbital can hold 2 electrons. The P block has 6 columns, and it can hold, the P can hold 6 electrons. The D block consists of 10 columns, and the D orbital can hold 10 electrons. And the F block consists of 14 columns, and the F orbital can hold 14 electrons. Coincidence? Not on your life. And actually, you can now utilize the periodic table to figure out electron configuration without using the mnemonic that you were shown a couple of videos ago. And if you're interested in learning how to do that, come see me. I'd be happy to show you. So let's review what came out in this video. Valence electrons are the electrons in the highest primary energy level. That's when the atom is in the ground state. At most, you can have 8 valence electrons, and valence electrons are always in the S or P orbital. The periodic table can be broken down into blocks based upon the electron configuration. The S block has 2 columns, column 1 and 2. The P block has 6 columns, 13, 14, 15, 16, 17, and 18. The D block, also known as the transition metals, have 10 columns, and those are columns 3 through 12. The F block, or the 2 rows under the periodic table, have 14 columns. Those are actually unnumbered. And what's not reviewed, and is really the take-home message here, elements in the same group have similar chemical properties because they have similar electron configurations. As we'll begin to talk about in the next section, all chemistry occurs with the electrons, and therefore the electron configurations are crucial to understanding chemistry. So you can smile now. You've finished another section, complete the various worksheets, take the exam, and then we can move on to making compounds as we talk about ions and ionic bonding and other types of bonding in the next section.